Recording in progress. Okay,
Recording
so
in
I'll very
progress.
slowly get started. I think everyone probably knows who I am. If you don't, then well, you'll know very soon. So I'm going to talk about today, presumably Brownian motion. Most of the time we're going to spend just talking about random walks, and random walks on Z and ZD. So nothing more complicated than that. Although that's already sort of pretty complicated. So we'll spend most of our time there, and then hopefully at the end we'll be able to try to define what a Brownian motion is. And I claim that it would be an example of something we'll call later a martingale. Probably Zach next week will touch more on that.
If you can hear me, then the answer is yes, I will be doing that.
Yes, we can hear you. So good. Excellent. So random walk. So I have we're going to start with the random walk on the line. So the first thing we're going to talk about is random walk on, I'll call it Z. So it's just a random walk on the line. I'm allowed to move. So what's the idea? I start at time t equals 0 well, at the origin. So my red dot, I should change the color of all these other dots. My red dot at the beginning is my starting point. And at each time step, so at time t equals 0, I flip a coin, and with probability 1/2, I move to the left 1 step, and with probability 1/2, I move to the right 1 step. So we're only going to talk about random walks that have equal probabilities in both directions, although we could talk about more complicated things, but just for the simplicity of exposition. So with probability 1/2, I move to the left plus delta x, and probability 1/2, I move to the right minus delta x. So at the next time step, t equals, I'll call it delta t. What position am I at? Well, I'm either here or I'm here, each with probability 1/2. So I'm here with probability 1/2, and I'm here with probability 1/2, which is, obvious enough from what I just said. So I repeat this process. So the random walk is just the repetition of this process for, ever. So the next time step, I'm either here or here. If I do this again, well, if I flipped the coin and I landed here first, when I flip the coin again, I'll either move this way or that way, each with probability 1/2, but it was a probability 1/2 to get here to start with. So the probability of ending up here after 2 coin flips is 1/4. And the probability of coming along this path from here to there is also 1/4. But it's not the only way I can arrive at this position. Let me color it in. So I can also arrive at that position, the one in the middle, by first traveling along. Well, if I flipped the coin and I got right on the first step, and then I flipped again and I got left, well, I would still end up here. Yeah. So, well, this path also contributes a factor of 1/4. So the total probability of being at the origin after 2 time steps is, well, 1/4 plus 1/4, which is 1/2. And then, here, I have a probability of being here 1/4, just like it was over here. So the general question that we kind of want to ask for this process, you write it in blue, is after time t has elapsed. So notice that t is measured in discrete increments. I have t is equal to 0, t is equal to delta t. The next time step is t is equal to 2 delta t, 3 delta t, so on and so forth. So after time t has elapsed, what is the probability I'm at site? X. And again, x is measured in increments of delta x. So here is the position: 0 times delta x, plus 1 times delta x, plus 2 times delta x, minus 1 times delta x, minus 2 times delta x, so on and so forth. So this is sort of the fundamental question we want to ask. And then we can ask some more precise questions shortly. So of course, this is a function which depends on, well, the position and t, and I can represent this probability in terms of this function. So my job really, the answer to this question will be to determine what this function looks like, u of x and t. So u of x and t, again, is the probability that, all right, I'm at site x after t time steps. T time steps, or after k delta t time steps. So maybe I'll write after time t has elapsed. It's maybe a better way to write this. So after time t has elapsed. So far so good. if there are any complaints, questions, comments, speak up. I like being interrupted. So, okay. So what does this function look like? How can I describe this function? Well, there are several ways. So the first way, which I claim is maybe the least useful, but sort of the most intriguing, is that I can write u of x and t. So let me label this ways to write u of x and t. And then we'll talk about its properties. So different ways to write u of x and t. Well, one way, which is, again, probably the most intriguing, but the least useful, is I can write u of x and t as the sum over all paths L from 0 to position x.
Good question. Hello?
Sure.
This is Alice. Yeah.
Hey, Al.
So yeah, so what do you define like U00?
0, 0 is going to be 1, so probability 1. I started the origin.
Probability ones. Okay.
Right, so u of 0, 0 is 1, and u of 0, anything else is going to be 0.
Okay.
So it's like
Thank
what I would call Kronecker delta function in some sense. So I start with probability 1.
You
So again,
start with probability 1. Okay.
right, at the origin, and then I propagate down. So how do you write it? Suppose, actually, it's a good question. We'll touch on it in a second. So what happens if I didn't start at the origin, but I had some distribution of probability that I started with? So I start maybe here with probability 1/2, here with probability 1/4, here an 1/8, so on and so forth. How do I describe that probability distribution? Well, we'll talk about that in a second.
Okay. Thank you.
Sure. So one of the most interesting ways, I think, to write this function u of x t as the sum over all paths. So L is a path from 0 to x, 1/2 to the length of the path. So just a dumb remark, note that the length of the path is just the number of time steps that have been elapsed, So t over delta t. So it's just a number of time steps. So just to see why that's true, let me scroll back up just to show you the picture. So we saw it sort of already by example. To get to this position, I have probability 1/4. So that's exactly one contribution, but there's only one path of length 2 starting from here, going to here. Same with this position. What about this position? Well, there are exactly 2 paths from here to here and from here to here. So I sum, well, 1/4 2 times, and I get, well, 1/2. And similarly, if I did the next level up, so if I did 2 time steps, let's just do one particular position. Let's do this one, for example. Well, what are the ways to come to this position of length 3? So I could either do this, that's one possible path, or I could do this, that's 2 possible paths, or I could do this, 3 possible paths, and I think that's it. So 3 paths. So it'll be 3 times an 1/8. So times 1/2 to the third, which is 3/8. So the probability to land at this site after 3 time steps of the last is 3/8. Because again, there are 3 paths that start here at 0 and propagate to this point. So anyone that's taking a quantum mechanics course, I think there's one person in the audience, will recognize this sort of being analogous to something like, well, Feynman's path integral and the definition of the propagator. So I'll use that motivation to call this thing something like a propagator. So kind of very interesting looking formula. The only reason I wrote it is just because the interpretation is useful, but it doesn't really help us too much because again, well, there's only so much we can do with this formula. It's nice, but we actually still have to count all the paths starting at the origin and eventually propagating to that point. So not super useful. What other, well, definitions of this function do we have? Well, another way to write this function, I was doing in blue. I can write u of x and t as, well, it's actually the same thing as above. Just the number of paths of length t over delta t, which is just the number of time steps from 0 to x. So the number of paths of that length of length t over delta t divided by the total number of paths of length that. Number of paths of length t over delta t. So that's just all paths, and we know just because from what I was talking about up here that number is 2 to the L. So there are 2 to the L possible paths of length L, just because there are 2 to the L choices you can make at each step. So another way to write it, and again, just as useful as the first way, just because you still have to count the number of paths length, well, t over delta t from 0 to x, which again, unless you're a combinatorial genius, maybe isn't such an easy thing to do. And especially if the expression, well, we don't use just the line, or we do the square lattice, maybe not so easy to compute, but useful interpretations nevertheless. So we want to eventually be able to compute u of x and t explicitly, or as explicitly as possible. And there's standard ways to do it. Actually, the combinatorics here isn't too hard, but one of the things I want to talk about today. So there are a couple of things I want to talk about. So today's talk will contain, I'll call it a functional and a Fourier analysis way, maybe is a better way to put it. For computing u of x and t. So that's one thing I want to talk about. The other thing I want to talk about is a more general question. So a natural thing to ask is, well, what is the probability, something we can ask about this random walk, what is the probability that it actually returns to the origin ever, say? Well, here, clearly it returns after 2 steps. After 4 steps, well, we won't ever end up here, but maybe after, 3 steps, but after 4 steps, we'll probably end up back in the origin. How often is it, will a Brownian motion visit the origin? How likely is it that it will visit the origin maybe infinitely often? Well, in 1 dimension, it turns out it's infinitely often. In 2 dimensions, same story, it'll visit the origin infinitely often. And well, if it's not either of those cases, if we're in 3 dimensions or higher, well, the probability of recurrence is no longer infinite. It may only visit the origin a finite number of times and then never return ever again. So this problem is called recurrence of random walks. So that's another thing I want to talk about. And we're going to use sort of this technique we found here to actually be able to answer this question. So recurrence of random walks, what is the probability of returning to 0? I guess while returning, right? Returning to 0 after n time steps, or after, maybe all right, returning to 0 infinitely often. And I think I put the quote in my abstract. So it's a quote of Kakutani's. I think it was at some, I think it was a UCLA seminar. He said, a drunk man always finds his way home, but a drunk bird may never return. Something like that. And that's exactly this, answering this question in layman's terms. That a drunk bird, a Brownian motion in 3 dimensions may never return to the origin. So it'll come to the origin, maybe it'll visit 3 or 4 times, but it'll leave forever. As opposed to in 2 dimensions or lower, like a person can only walk on the ground. You'll visit back to where you started infinitely often. So you always come back home if you started at home. Okay, so that's another thing I wanted to address. A couple other things I think I wanted to talk about. Let me see. So we'll start kind of hinting at what the continuum limit should look like. Of a random walk looks like. So that's sort of the last thing I want to talk about, and then we'll kind of give a bunch of properties that will kind of set up the definition of a Brownian motion, and then maybe next time I talk in a couple of weeks after Zach is done defining martingales, we'll actually kind of delve into Brownian motion, calculus, all that nonsense. So before doing any of that, I do actually want to address something about the last point first, because it's sort of something we'll kind of want to keep in mind for the remainder of the talk. And it'll kind of, well, this relation will pop up often. So first, notice the following about the function u of x and t. So suppose I want to compute u of x and t plus 1. So that is to say the probability that I might cite x after t plus 1 time steps. So let me draw. Here is time t plus 1, sorry, t plus delta t, I think was what I was calling it. So plus delta t. So here's time t, here is time t plus delta t. And maybe I'm at this site. So let me draw a couple dots here so I can fill things in. So maybe, I don't know, I start here. So this is the side I'm at. This is u of x and t. So this is position x. No, sorry, that's not what I want to write. This is position x at time t plus delta t. And I want to know the probability that I actually end up at this site. Well, where do I have to be at the previous time step for me to actually end up at this site? Well, I can't be here because if I'm here, I have to go there or there. I can't be here because I can't even reach x. I can't be, here because I can't reach x again. The only places I can actually reach x from are this point and this point. And well, I know the probabilities of being at those sites. So this is position, this one here is position x plus delta x. This is position x plus x minus delta x, sorry. And so I end up with this nice relation that u of x and t plus delta t. So the probability of being at site x after t plus one more time step is just, well, 1/2, because every time I move down a level, I have to multiply by 1/2. So it's going to be 1/2 times u of x plus delta x and t plus, write that a little bit cleaner, plus u of x minus delta x and t. So the 1/2 again, because I moved down a level. So nice relation. And if I manipulate a little bit, not too much, I'm just going to subtract from both sides u of x and t. So on the left-hand side, I have u of x t plus delta t minus u of x and t. On the right-hand side, I have 1/2 u of x plus delta x and t plus u of x minus delta x t minus 2 u of x and t. Does anyone do numerical analysis kind of things, or does anyone recognize this sort of expression, how they look similar, both sides, or what either side looks like? Any suggestions from the audience? Yes, no? Louis, I see your camera is on. You want to say something?
Well, it's a heat equation, of course. But
It's a heat equation. So who was that? It sounded like.
no, who was that? Who do you think was that?
Yeah. No, it's a good observation. It kind of looks like, so this sort of looks like, well, a difference, a single first order difference in time. So it looks something like du dt. And this looks something like a second order difference in x, which is something like du dx squared, sorry, and then with the 1/2 up front. But this really only happens if I have a particular scaling between x and t. So this is the first hint at the sort of scaling we want to expect between x and t. So if I do want to actually end up with something like the heat equation in the limit, so I want the limiting function to actually be well defined, that I end up with something that will make sense. I require the scaling that delta t goes like delta x squared. This squiggle just means delta t is equal to a constant times delta x squared in my notation. So delta t should go like delta x squared, because I need to divide by delta x squared on the left-hand side to actually get a second derivative, and not something that either blows up or is 0. And on the right-hand side, if I divide by delta t, well, So in order to get a well-defined, interesting limit in some sense, this is the scaling I need. So I need that delta t scales like delta x squared. So this scaling I claim is very important. We're going to come across it a couple of times. So let's just keep that in mind. So right, I had a couple of things I wanted to address. One was this Fourier analysis technique for actually computing the function u of x and t. So we'll talk about that first. Then we'll go on to actually talk about recurrence of random walks using the thing we found. And then finally, we'll end by kind of hinting a little bit better about what the continuing limit should look like. And then we'll actually realize that well, the thing we found in the recurrence about recurrence holds in the continuing limit. Not too deep a result. So let's begin. So what did I say? I said Fourier analysis technique for computing u of x and t. So I think that I find it easier to actually do that. Let me think. Right. So how do we actually calculate u of x and t? Well, for a second, let's talk about a different problem. So let's talk about this Hilbert space. So this is L2 of z. It's a set of all sequences, two-sided infinite sequences. So I'll call them AKs, such that the sum AK squared is finite. So this is little L2 of z. Those of you that are familiar with Fourier series, it's just the set of Fourier coefficients of nice functions, L2 functions. So it's a Hilbert space. What's the inner product on this Hilbert space? Well, if I choose sequences AK and BK, the inner product on these two things is just, AK, BK bar. Okay. So let's pictorially represent this Hilbert space. So the Hilbert space has a countable basis, which is nice for us. And I can label the countable basis by, well, basis vectors, E0, E1, E2, E3, E-1, E-2, E-3, so on and so forth. So the J's represent the jth element of the sequence. So E0 represents the element in the middle. So I have an infinite sequence. How do I write? A-3, A-4. I need to go off in this direction. A-4, I guess, A-3, A-2, A-1, A0, and all the way into the other direction. So the E0 basis vector is the vector that corresponds to this element. The E-1 basis vector is the one that corresponds to that one, so on and so forth. So on this Hilbert space, I'm going to define an operator in an obvious way. I'm going to define the right translation operator, which maybe I'll call not U. No, I'll call it U. U, which on the basis element EJ is defined to be EJ plus 1. So what does it do? It takes the basis element or basis vector at EJ, like this one, and sends it to EJ plus 1. So it's an operator in Hilbert space. It's nice, well defined. And I can even define its adjoint. So the adjoint of this operator is on EJ minus 1. So you can check by using this definition of the inner product, or you can just take my word for it that the adjoint of the right shift operator is the left shift operator. Okay, so now let's start playing a game. So I'm going to define a new thing. What did I call it in my notes? I think I called it P. P, which is 1/2 U plus U star. And let's play this game where I apply P to the basis vector E0 and see what happens. Well, the first time I apply P, what happens? Well, this is just 1/2 U plus U star applied to E0, which is what? Well, it's going to be E1 times 1/2 plus 1/2 times E minus 1 by the definition of what these things do. Okay. Well, we could even stop there and just claim that everything else is very transparent. But let's go a little bit further. So let's go one more step. P squared E0 and see what happens. So well, this is just going to be 1/2 U plus U star applied to, well, this pair of vectors now, 1/2 E1 plus 1/2 E minus 1, which is going to give us what? We'll have 1/4 times E2 plus 1/4 times E0 plus 1/4 times E0. So one of these is coming from this applied to, this applied to this, and this applied to that, so the cross terms, and then finally plus 1/4 E minus 2, which overall gives us, well, 1/4 E2 plus 1/2 E0 plus 1/4 E minus 2. So does anyone recognize the coefficients of these basis vectors? If you don't, it's fine, but I'll tell you what they are. If I go back and actually look at what I was doing before, they're precisely the probabilities at time, well, at the kth time step. So in this case, the second time step. So it's 1/4, then I'm at site 2, minus 1/4, then I'm at site minus 2, and then 1/2, then I'm at site 0. Same here, and then same there. So what I'm actually finding is that if I apply, so I'll write down the principle. And so you can even prove if you want, but I'd like to be formal here. So what we're noticing, the coefficient of EJ of the vector U to the K E0 which I'll call V, is just the probability I'm at site J after K time steps. So in other words, this function u of x and t, which I'm now going to write, so I'm going to change from writing x to p to the k. Thanks.
Yeah.
Thanks, Zach. P to the k. Good catch. So this function u of x and t, which I'm now going to revert to calling them k, which is just the multiple of delta x. Yeah, Zach, you're amazing. And t, which was well, I can't use k there, so I call this site j, and this is k. So it's just this function that we started with. This is in so j times, maybe I will write it. J delta x, k delta t. And sorry, I might be, I just realized I might have been doing that. I might have changed which variable I called, or which position I put x and t in, but hopefully it's okay. Everyone kind of follows what I'm talking about. X and t are first here. Did I ever do t and x? So maybe I'm okay still. Okay, so maybe it's fine. I did that in my notes last night. I should interchange the position of x and t, and everything got mixed up. But anyways, so actually, interesting fact that we can actually compute this function u of x and t almost by just looking at the coefficients of this thing. So how do I actually compute, well, this function u of x and t? Well, how do you find the projection of, I kind of gave it away. How do you compute the jth coefficient of a vector? Well, you just project onto that vector. So this is precisely well, ej, p to the k, e naught, and the inner product is in L2 of z. So what have we done? We've actually discovered a way to actually compute, well, I wouldn't say actually discovered a way to compute, but we found a different way to realize these transition probabilities. The probabilities being at site k or at site j after k time steps. Now, again, not super useful because again, it's just as hard as counting the number of paths. I mean, to compute this inner product, you still have to count the number of paths. Not great. But we're cleverer than that. We know a little bit of Fourier analysis, and we know this thing called Parsifal's theorem. So let me write Parsifal's theorem for you. So if f and g are functions from L2 on the circle, and I denote their Fourier, well, then there's a nice map into Fourier coefficients. So f hat n's are just the Fourier coefficients of f. So f is some of these things, e to the I n theta. G is some g hat n, e to the I n theta, and f hat, g hat are in little L2 of z. And furthermore, the inner product of f and g in capital L2 of the circle. So capital T is just a circle, it's just Fourier series. And its inner product is integral 0 to 2 pi 1 over 2 pi f g theta. This is the same as this. So why is it useful? Well, I have this, and maybe it's not so easy to compute. And I have this, which maybe isn't so easy to compute, but I claim that it is. And why? Well, because we know how to compute integrals, whereas we may not know how to count that well. So we know how to compute integrals. And this integral is actually going to be particularly easy to compute. So if I actually transfer this to its corresponding Fourier series, well, ej, what does ej become? Ej is sent to e to the, maybe I shouldn't use j, but I, j theta. So maybe I'll call it something else besides j. What have I not used? N, m. This thing, we don't really know, but we know how to compute Fourier transform of an operator in some sense. So p to the k goes to, well, 1 over 2 to the k, e to the I theta plus e to the minus I theta. These correspond to the left and right shifts. And then, well, E0 goes to 1. So at the end, what integral do we end up with? So I'll write this. So we end up with, I'll write it on the next page. So we end with the following formula for u of, and I think I'm going to change what I'm calling variables again. So k delta x, n delta t, maybe, I don't know. is 1 over 2 pi, 1 over 2 to the n, the integral from 0 to 2 pi. And then I have e to the minus ik theta. And then what do I have here? I have e to the I theta plus e to the minus I theta to the n. And I can even write this as a residue theorem type integral. 1 over z to the k, z to the, or z plus 1 over z to the n. Which, if you use binomial expansion and, well, that's it. Binomial expansion, residue theorem, the result is immediate. And I'll give you the answer. Hold on. I don't think I actually wrote the full answer because I was only interested in one case. But for example, if I pick k to be 0, what do I end up with? Well, I'll end up with, where did I write it? That is the real question. Here, u of 0 and n is 1 over 2 to the 2n, 2n choose n, and that's it. So this just comes from, well, explicit computation of this integral, which I don't know, maybe to you it's not the nicest expression, but to me I'm much more comfortable with doing Fourier series things than I am with combinatorics. So it's just an interesting way to compute things. And actually, sort of the motivation for doing things this way is it actually allows you to kind of introduce more complicated boundary conditions where the counting might be harder. So for example, similar techniques allow you to compute, well, the return probabilities for things like a random walk on the half line. So what do I mean by half line? There is wall here, and if the Brownian motion runs into the wall, or the random walk runs into the wall, then it dies, it gets killed. Now you can also do this on more complicated spaces. So the same technique applies to, I did L2 of Z. I could do L2 of ZD, and I have TD here. So I still have Fourier series, and so I can still compute a Fourier type integral and end up with the return probabilities in n dimensions, or u of k and t in n dimensions. So my point here, and the emphasis, the thing to take away, is that it's just a useful way to actually compute the return probabilities that has only to do with Fourier analysis. You don't have to know much about combinatorics. You just have to be a little bit clever with your functional analysis tricks. Right. So part of the question we were trying to answer from the beginning was about return probabilities. So we wanted to know, well, what is the probability that a Brownian motion, or a random walk, I keep saying Brownian motion, sorry. A random walk actually returns to the origin and returns infinitely often. Well, we already know how to answer the question, what is the probability of returns at time t? I just put x is equal to 0 here, and that gives me the probability that returns at time t. So how to compute, well, one object that we need in order to compute this recurrence is going to be the function, which I label here, u of 0 and n, which I actually have a name for. It's going to be r, I'll call it 1 of n, and this is probability of returning to the origin after n time steps. So I can similarly define these things for d-dimensional lattices. So for the one-dimensional lattice, we actually just computed. This is it. For the two-dimensional lattice, similar techniques. So this is the same probability, but I'm now allowed to move in two different directions. So the picture here is, I have square lattice now. And at each time step, I can move in one of four directions with probability 1/4. I start here, and I either go up, left, down, or right. And then, continue in this fashion. So maybe if I ended up here, I would go either up, down, left, or right, and so on and so forth. So this again is the same thing, and I can define it in d dimensions or d of n. So the only ones I really cared about that we need to actually answer the question that we originally wanted to know is in 1, 2, and 3 dimensions. So we only need to know what they are in 1, 2, and 3 dimensions, and I'll actually write them out for you. The one in 2 dimensions, you can compute by the same technique because, again, it's just Fourier series, just in 2 variables now instead of 1. 1/4 to the 2n. 2n, choose n squared. So interesting remark about this before I move on. How does it compare to the one-dimensional one? Well, any takers? How does it compare to the one-dimensional one? So the two-dimensional return probability How is it related to the one-dimensional return probability? Well, it's fairly obvious. This is just the square of that, yeah? Looks like a square, yeah, exactly. Does it happen? Would you expect then that R3 is the Q? So I have a question for you. Is it going to be 1 over 2 to the 2n cubed? 2n choose n cubed?
No.
Who says no? Hunter?
Yeah.
Why?
I have no justification.
No justification, just a guess.
Just a guess.
Zach says doubtful. He's experienced something. My experience isn't that nice. Yeah. So it isn't, and there's actually a reason that this happens in 2 dimensions and not in 3. We'll talk about that in a second. So let me write what the 1 in 3 dimensions actually looks like. So it's actually well, the coefficient out front is the same, 1 over 6 to the 2n. But the actual expression is a little bit different. It's going to be sum on j and k, 2n factorial over j factorial. This is j k from 0 to n. J factorial, k factorial, n minus j minus k factorial. What was I saying? Or j plus k is equal to n. Sorry, so j plus k is equal to n is the sum. So hey, talking. So right. So it's not the square of this one, but maybe we can actually answer questions about return probabilities now. Yeah. Sorry, got distracted. So a couple of things I wanted to mention. One was the relation between this and this. And then the next is just going to be how to actually compute the probability of, well, recurrence that I return to the origin infinitely often. We can use that, or we can use these expressions to actually be able to compute that, which I'll talk about briefly. So maybe first and foremost, let's talk about the relation between R2 and R1. Anyone know why this is the square of that one? Because this clearly isn't the cube of that, and these two don't seem to be as nicely related as you'd like. So why is this the square of that? Anyone know? Unfortunately, no. Maybe there is no reason. Maybe it's just coincidence. Who thinks it's a coincidence? Anyone? No one says it's a coincidence, so maybe it's not. Maybe there's something to it. And there sort of is. So the idea is the following. A geometry thing, kind of, sort of. So I take 2 independent copies of one-dimensional Brownian motions, or sorry, random walks. So 2 independent. I don't think I spelled independent right, but it's too late now. Independent copies of 1D random walks.
And they're perpendicular to each other.
Right, so I draw them in this perpendicular fashion. So what happens? Well, at the first time step, the first one either moves this way or that way. And the second one either moves up or down. But I take as coordinates of my 2-dimensional random walk, well, the coordinates of the first one, and then the coordinates of or the value of the second one. So in other words, I'm at one of these 4 positions, 1, 2, 3, 4. So I take the coin flips as my coordinates of my new position. So I end up here, 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 here. So I've moved sort of vertically. The next time step, what do I do? Well, same procedure. I either go up or down, left or right. And so I end up with, well, this family of positions. Like that, or I could go back to the origin. And it continues in this fashion. So what I actually end up with is sort of like if I look at it sort of diagonally, it's still 2D Brownian or 2D random walk. It's just on this slightly scaled by √2 lattice. So if I wanted to be precise exactly, I need to scale everything by √2 back. But it's exactly the same thing as a 2-dimensional random walk. It's just rotated 45 degrees and then scaled up a little bit. So taking 2 independent random walks, well, probability of returning to the origin is just probability of each of the independent coordinates being 0. So I just take the product of these probabilities because the 2 results are independent, and I get the square. So that's where that comes from. So it's not a complete coincidence. And well, exercise for you, think about why that doesn't happen in 3 dimensions. So why does it happen that I can actually write the product of 2 independent random walks and I get 2-dimensional random walk in 2 dimensions? But if I take the product of 3 independent random walks, what do I get? Well, it won't be, according to this formula at least, a 3-dimensional random walk. It'll be something else. So okay, let's try to answer the question about recurrence now. So again, the question about recurrence, I'll remind you, was just the probability that a random walker in d dimensions, this is in 1 dimension, 2 dimensions, 3 dimensions, actually returns to the origin after d time steps. Or I'm sorry, not after d time steps, but returns to the origin infinitely often. Let me find where I am in my notes because I skipped around a little bit. Right. So I think we can actually rely on one result from Lewis's talk last week. It's not anything deep. It's just going to be Stirling's formula. So from Lewis's talk, Stirling's formula we'll need, which says that n factorial goes like root 2 pi n, n over e to the n. And we also need, well, eventually we'll need to write out, we'll use this expression to write out the asymptotics of each of these things individually. And don't worry, I won't do it explicitly, so you don't have to sit through me trying to calculate things for 15 minutes. So my first claim is on one of these pages. Let me find it. Here, I think, yeah. So we need this result in my fact that I'm going to reference, which is more or less a self-obvious fact, is that a Brownian motion, or random walk, sorry, random walk returns to the origin infinitely often, if and only if the following sum is finite. So RDN blows up. So if it's infinite. So in other words, it has non-zero probability at every step. The probabilities don't go to 0 is a good way to think about this. So the probabilities don't shrink, they blow up. And they blow up fast, kind of. Maybe not super fast. So this is an equivalent way of formulating this question, that we just sum up the RDs. And if it blows up, well, then the random walk was recurrent. It returned to the origin infinitely often. So actually, we can use Stirling's formula and these formulas we have for R1, R2, R3 to actually get a good estimate on what this sum looks like. So in 1 dimension, Stirling's formula tells us that, so this is Stirling's formula. This is the expression for u of 0 and n. And what we find is that R0, 1, and n, I'm going to write, goes like, so I don't have to be too precise. What is it, 1 over n to the 1/2? So in 1 dimension, what happens? Well, this sum, if everyone remembers what a p-series is, blows up. So indeed, in 1 dimension, what we conclude from this is that in 1D, a random walk is recurrent and visits 0 infinitely often. What about in 2 dimensions? Well, in 2 dimensions, similar analysis, and I'm kind of leaving out the details, but it's just a matter of well, taking this expression, plugging it into n choose k, and then moving things around. What do you get? So you get, well, it goes like 1 over n. And well, this still blows up. So still no good, still blows up. Well, still good, I guess, in some sense, though. The random walk will return to the origin infinitely often. So in 2D, it's also recurrent. Also recurrent. Well, I only have 1 more dimension to check, although we can check as many dimensions as we want after this. So what happens in 3 dimensions? So if you check standard probability theory books, typically the way they do this is they make an estimate for it. So they don't directly apply Stirling's formula. For the first 2 cases, it's relatively simple because there aren't so many terms. Here you got a lot of n choose k's, and you still have to sum some things up. So maybe not the best procedure, but in principle, it still works. And there are some estimates you can make to get that, well, this term that I'm about to write down goes like 1 over n to the 3/2. So in fact, in 3 dimensions, what happens? Well, this sum is actually finite because, this is when I sum these things up, I get something that's not infinite. So in fact, in 3 dimensions, well, what we find and actually in higher dimensions as well, random walks are not recurrent. So in higher dimensions, random walks aren't recurrent, and well, a return to the origin happens only finitely many times before you leave forever and never come back, at least with non-zero probability. So I think that covers the question of recurrence. I was a little formal, but I don't want to give too many details about well, how to actually do the computation, just because it's not particularly clean and it's not particularly enlightening. The idea is really what's important here, that you can well, compute the return probabilities using this nice technique up here, if you so desire, or you can use them however you want. Then you have these expressions for the return probabilities. And then you can use something like Stirling's formula or estimates to actually determine whether or not the Brownian motion returns to the origin. N goes from 1 to infinity. Yeah, but so good point. Thanks for that. That's a good point. 1 to infinity. Otherwise, well, they're all infinity. Yeah. But at least the first two were still technically true. Yeah, they're still technically infinity. It's just not what I meant. But yeah, good catch. So right. I think that's what I wanted to say here. So yeah, that covers recurrence. So I think there was like one last thing I wanted to talk about, and then we can kind of be done for the day. So the last subject, which is really the last two, if I go all the way back, so today's talk. So we covered, check it off. We covered Fourier analysis techniques for computing u of x t. We talked about recurrence, and now I want to sort of hint at how the continuum limit should look. And we already got our first hint down here, so maybe I'll copy this over. That well, the function u of x and t, if I expect it to have a proper scaling, so if I take limit as delta x goes to 0, delta t goes to 0, well, I can't just do it in any way. I want a proper scaling to exist. And the only proper scaling I can have is that, well, delta x squared goes like delta t. And we'll just pick the constant in front to be 1 just for simplicity. So if this happens, if I pick this scaling, so choosing the scaling, this, well, the function u of x and t actually has a nice well-defined limit. And what is it? Well, it's du dt is equal to 1/2 d squared u dx squared. And I think Dima already told us what it is, but anyone recognize the equation besides Dima?
He said it was heat equation, yeah.
That's the heat equation. And so I should make a remark. I talked about random walks in higher dimensions. There is a similar function, of course, and it will satisfy a similar equation. You have different directions you can travel along now. So instead of getting just du dx squared in 2 dimensions, you'll have so the 2D version. This is 1D. Is going to be 1/4 d squared u dx squared plus d squared u dy squared. 3D an eighth d squared u dx squared plus d squared u y squared plus d squared u z squared, so on and so forth. You kind of get the idea. So it's always described by the heat equation. The left-hand side is du dt, and the right-hand side is Laplacian in that particular dimension. So the limiting distribution of a random walk is described by, well, it's described by this function. What am I saying? The limiting distribution is described by a solution to the heat equation. So the fundamental solution to this equation, so a little bit of knowledge of PDEs is required here, but it's not difficult to check. That is the solution that we were looking for. So our solution U, which had all of the initial mass at 0.0. What does it go to? Well, it goes to this function, and let me make sure you get all the constants right. So U of x and t in d dimensions now is going to be 1/4 pi, I'll call it capital D to the t, to the d over 2. I was using n dimensions for, so maybe I'll stick with n for my notation. And e to the minus x squared over 4 dt, where d now is 1/2n. So this is the solution in n dimensions, the fundamental solution. This is what the distribution of mass looks like. At time t equals 0, I have this, well, you can see that it sort of blows up, but it's like delta function sort of spike. All of the mass is at the origin. I start at the origin and everything kind of spreads out after that, like a Gaussian. So in some sense, we actually got central limit theorem sort of out of this. We end up with Gaussian for a bunch of non-Gaussian variables, like Bernoulli type variables, I'll call them. And we actually also end up with something that we sort of already saw. Look at the coefficient. So when x is 0, this piece doesn't matter at all. Look at the coefficient. And look at its behavior as a function of t. It goes like n over 2, yeah? 1 over t to the n over 2. Well, when is that integral convergent over a positive interval? I need to regularize. I need to ignore what's happening at 0. But as long as I regularize appropriately, look what happens. The scaling law is exactly the same as it was in each dimension that was here. So here I had n to the 1/2, 1 over n, 1 over n cubed. So that's exactly where that's coming from. So we could have guessed if you knew something about PDEs. Well, where a random motion is actually recurrent by just looking at the fundamental solution of the heat equation in that number of dimensions and looking at, well, this piece of the coefficient, the relevant piece. So that's nice. We kind of expect that. So the thing to take away at this point is that we sort of expect that if a Brownian or a random walk has a well-defined limit, which I keep saying Brownian motion, we might as well call the limiting thing a Brownian motion. Well, if this limit exists, we're sort of kind of coming across properties that it should have. So first of all, if the limit exists, we expect that the scale between x and t, the continuum scale between x and t, should behave something like this. And in fact, we sort of see that reflected in the solution, the fundamental solution to the heat equation. Notice that, and how I want to write this. Where did I write this is the real question. Not there, not there, not there. Is it on this one? Yeah, no, it's not either. Where's page 6? 6 here. Right, so notice that if I send x to ax, t to a squared t, and u to au, the solution remains invariant, doesn't change. So somehow it reflects this sort of scaling behavior that we already kind of initially expected, which we kind of built into the problem to start with. But we still are describing only, this is a deterministic equation, yeah? This is a probability, it's completely deterministic. We still want to describe somehow the stochastic version of this thing. And maybe that's what we'll end with today. So we sort of hinted at what sort of properties the continuum process should have. But now we need to be a little bit more precise about the actual process itself. So we spent a while investigating all these properties of random walks, how their scaling limits should look. Now let's try to give a rigorous definition of what the continuum object should have. So how do we define the Brownian motion or a random walk in the first place? Well, I had a sequence of variables, xk's, random variables, independent random variables, which I was taking to be coin flips, such that, well, the probability of moving to the left, or right, I guess this is 1/2. The probability of moving to the left is also 1/2. And we can think of xn as representing the decision at the kth time step. So they're all independent coin flips, and each of them is with equal probabilities. It's a fair coin. And how do I describe the position of the random walker after k time steps? Well, the position of the random walker is just described as, well, the sum of all the outcomes of each of the individual trials, or each of the individual motions I make. So what's the sorts of properties? Sn is sort of the object I'm interested in. This is what I would end up calling the random walk, because it describes the position of the random walker after n time steps. So this function u of what was I calling it? K delta x n delta t is precisely the probability that Sn is equal to k delta x. So this is exactly this function from before. So it's exactly this probability. Sn is describing this thing. It's like the distribution function of Sn. So what sorts of properties does Sn have? Well, first of all, it's centered. So it's mean. If I take its average, I get 0, which is clear because, well, the sum of expectations is the expectation of sums. And each of these is a centered variable. They each have mean 0. What about the variance? Well, if I actually compute, I'm going to get delta x squared. But this is the same thing by the scaling law we imposed before. It's delta t. So it's just the step size delta t. Sorry, n times delta t. So n delta x squared, n delta t. So it's exactly the amount of time that's elapsed. Okay. maybe n squared delta t, I forget now. Furthermore, if I take this difference, Sn minus Sm, if m is less than or equal to n, so what am I looking at? I'm looking at what does Sn minus Sm contain? What contains the last n, or m plus 1 to n
The tail.
steps, yeah, tails. And well, this is actually independent. It's obvious from this statement, but it's independent of the previous SMNML for L less than or equal to M. So it's independent of the previous tail of the series. And I can also look at the distribution. You'll find that the distribution of this random variable, this one, Sn minus Sm, is binomial, and binomial with width n minus m. Or maybe n minus m plus 1, but it doesn't matter too much. So all three of these properties are sort of telling us something about what we expect in the continuum limit. So in the continuum limit, what analogs should we sort of expect? So, and this is the last thing I'll say and I'll be done, what to expect in the continuum. Well, one, I expect that, I didn't really say it before, but I should start at 0. So the continuum random variable, which I'll call ST, ST depends on a continuous variable, T. So a continuous T variable, and it should be 0 at the beginning. It should have independent increments. So ST plus S minus S sub S is independent of S sub T S R for R less than or equal to T. So this is precisely mirroring this piece. And the increment should be, well, they can't be binomial, but what does the binomial distribution tend towards? Well, we kind of already saw here, it should tend towards Gaussians. So we kind of expect that they should have distribution centered Gaussians, and 0 T minus S, I think. How did I write T plus S? So just T. And finally, something that we were kind of taking granted before, because it was sort of a discrete process, so continuity didn't really mean anything, but we want the process, the paths, the sample paths of this Brownian motion, this process to actually be continuous. So we sort of expect S sub T to be continuous in T. Now it's going to be sort of badly continuous in T because it's going to be a very wiggly looking curve. Like if you've ever seen these pictures of Brownian motions, what do they look like? They look like, you know, this sort of thing. But we still expect it to be kind of continuous. You'd still be able to trace your finger along the curve, and well, nothing bad should happen. So in the interest of time, I'll say I'll stop there. But yeah, thanks. That's all I have to say for right now. And we'll talk more in a couple weeks about more precisely what I mean by defining a Brownian motion. This is actually what we're going to take as a definition, but well, we'll revisit it soon. So any questions?
Anything, cool talk. Can you go up, scroll up a little bit?
Here?
That formula right there, yeah. U of K delta X.
Mhm.
So you have probability of Sn equals K delta X, and XK are all Bernoulli variables, yeah?
Mhm.
So you computed this using this shift operator argument, but that's just binomial distribution. So why, at least in the one dimensions, couldn't you just use a direct combinatorics argument?
No, sure, you definitely could. And in D dimensions, you can too. It's just, for one reason, it's an interesting way to compute things. And two, it actually allows you to do, well, impose more interesting boundary conditions and still answers similar questions in cases where the combinatorics might be harder.
How would you do it? Is there, how bad does it get in the D-dimensional case and dimension greater than one?
I did it explicitly. It's not terribly hard. It's just some clever counting, but I claim that integration you don't have to think about at all. You don't have to think counting. You have to think.
Sure.
Integration, you can close your eyes and integrate. Yeah, at least I can. So
Okay, sure.
thanks. So any other questions? If not, then let's thank our speaker, and I'll stop the recording. So
Thank you, speaker.
yes.